starting lecture 6. Today we will continue with systems of equations. So we're going to look into some general conclusions, such as when does the system have a solution, when it doesn't, when it has infinitely many solutions. Then we're going to move to quadratic equations. So we know very well how to solve linear equations. So we're going to go to quadratic equations. So from now on, we're going to leave the simplest equations, and we're going to increase the difficulty a little bit and go into more and more interesting cases. And then my plan is to start inequalities. So we're going to start with linear inequalities, and then we're going to go to nonlinear inequalities based on quadratic equations, at least at first. So this we're going to do again if we have time today. We are doing fine with time in general in this course. So if we don't have time for this part, we're gonna kick this one off on Monday. All right. So in lecture 5, we basically finished powers, right? And we considered two cases: when powers were integers and when powers were rational numbers. And the main rules for both cases, they basically stay the same. So the main rules is if I raise anything to power of 1, I have the same number. So if I raise a to power of 1, that's just a. If I raise any number to power of 0, that's just 1. If I'm multiplying two numbers raised to to different powers, and importantly, those two numbers are the same, so they share the same basis, then I basically need to only add the powers. If I divide, then I subtract. And we had a couple of more rules, and those rules stay the same if we go to powers which are rational numbers. So we can raise any number a to power b over c, so it's a fraction. Of course, c cannot be equal to 0 because we cannot divide by 0. But then when we need to multiply, divide, and so on, we use effectively the same rules, some of which are aligned here. So the fundamentals do not change, even if we work with powers that are not integers anymore. Then we looked a little bit at linear equations, and well, this one was not surprising at all. So I think all of us are pretty good at solving linear equations. At least we know what they are. Basically, they have this form. We have known coefficients, a and b, and then we have the unknowns, x. And then how we need to find x? Well, we just need to shuffle things around, right? So we can move b to the other side. Then we move everything that depends on x to the other side, and then we just solve for x. That is it. So this one is quite obvious. One of the examples, let's say 3x plus 2 equals x minus 1. And exactly all we do is just moving things around. All the numbers go to right-hand side in this case. What depends on x, in this case just x, goes to the left-hand side. And then we just obtain that x is equal to minus 3 over 2. So this was more of a refresher for us to start looking into systems of equations. And the basic form was this. So we have a few known coefficients, let's say a, b, and c. And then we have two unknowns right now. We have x and y. And this is the case where we have two equations and two unknowns. And both of these equations, they need to be satisfied simultaneously. So x and y satisfy both equations simultaneously. That's the idea. Both equations. And we looked at two techniques in particular how to find x and y when we have two equations and two unknowns. So today we're going to work through a couple of more examples. We're going to practice a bit more. You're going to have exercises on Monday from systems of equations. So what we're going to do today, I want to have a look a little bit again into equations and powers. So we're going to revise powers. and we're going to look at a particular financial example. Then we're going to revise systems of equations. Then we're going to look into quadratic equations. And then, if the time permits, we're going to start inequalities. So this is the plan for today. If we do not manage to go to the step 4, that's totally fine. We're going to take it up on Monday. All right, so let us start with a brief revision of powers and also linear equations. And I want to do this revision through a financial example. So after all, we need to back up our techniques that we learned with some examples. And we're going to have a few lectures separately, just dedicated to solving examples related to economics, finance, and business. So we might as well just start here with like a very simple example. So I bet you also know such example anyway, but I just want to stress a couple of points, and I just want to use this example to illustrate a couple of ideas. So financial example on powers and also equations. So it goes like this. So imagine that you put 1,000 kroner into the bank. So 1,000 kroner goes to the bank, goes to a bank. And let's say that monthly interest rate is, I don't know, 5%, something like this. Okay? So what is the amount in 1 month? In 1 month. How should I calculate? I'm pretty sure that if you're taking finance courses, you probably have seen this. So where should I start? What should I multiply by something? Yeah? Mm-hmm. So it's 1 plus 0.05. Yeah, because it grows by 5%. So indeed, after 1 month, you're going to have 1,000, and you're going to multiply by 1 plus 0.05. So 0.05, indeed, it represents 5%. And we need to multiply, well, in this case, it's just 1 point times 1.05, because it grows by 5%. Had we multiplied by 0.05 only, it just gives us 5% of 1,000. But the 1,000 grows by 5%, so I multiply by this, and then I have 1,050. Okay? So then, what's about 2 months? If we kept on going in 2 months, all right? So just by following the same example, in 2 months, I guess we would take what we have in 1 month, and we just do the same computation again, because what we acquired after 1 month, then it's going to grow again after another month. So in 2 months, we're going to have 1,050 times 1.05, like this. But we can notice that this one, the first number, is just 1,000 times 0.05, right? So this and what I wrote in red, this is the same. And then I multiply it again by 1.05. So in a more handy notation, I can just write it as 1,000 times 1.05 squared. Yeah? So I can just write it by using powers. So this is after 2 months. Then naturally, in 3 months, I can follow the same chain of arguments. I simply take what I had after 2 months. So I take this part, and that's basically 1,000 times 0.05 to the power of 2, because it's after 2 months, and then it's gonna grow for another extra month. Right? So that's what it means. So 2 here means that this is what I have after 2 months, and this is another month. But this is just the same as 1,000 times 1.05 to the power of 3. So that's the same. So if I asked you in some arbitrary n months, in n months, how would this expression look like? Right? So we did 1 month, 2 months, 3 months, and I just say, I don't know, n, 50, 100. How would it look like? Yeah. Exactly. So the general formula in this situation is just 1,000 times 1.05 to the power of n. So we just need to take the number of months or periods. It really depends what situation you are looking at. It could be days, it could be quarters, years. So this is just periods. Depends on periods of time that you are talking about. So you just need to raise to that number. Okay. So a general formula for this would be the following. So general formula to figure out how much money you accumulated. It would be K times 1 plus P over 100 to the power of n. So this is the general formula. What are the components of this formula? Well, K is just initial amount, right? So in our previous example, that was 8,000. I just said, I gave you one, well, we start with 1,000. So initial amount. Now, N, we already discussed. It's the number of periods. So in this case, in the last example, we talked about months. So if it's 10 months, you write n equals 10. P, it's the interest rate in percentage. Interest rate in percentage. Right? So that's how, by using P over 100, that is how we converted from 5% to 0.05. So just to stress this one, that in our example that we had, P was equal to 5%. So to use 5% in this formula, we do 5 over 800, right? So P over 800, and it gives 0.05. Because I just write nominally 5%, but mathematically I need to multiply by 0.05, like this. All right, so this is just a general formula. And we can do many things with this formula. It can help us to answer interesting questions. first, we use powers. So that's important. We understood that all we do, we can just merge the number of growth instances into a number of powers. So that's very nice. And by using this formula, we can investigate in interesting situations. So from this formula, we can have a few examples. And with these examples, we can look into a couple of interesting equations. So for instance, the first question would be like this. So if we know our target savings, right? I know that, let's say in 10 years, I want to have this much money. If we know our target savings, and if we know interest rate, and time horizon, so in other words, N, so if we know this, we can find the initial amount. So if I know the time horizon that I'm looking at, I know interest rate, I know what I want to have in the future, I can figure out what I need to put in the bank. We can find the initial amount. Like this. Right, so I need a couple of things to do that. I know my target savings, I know the interest rate, and I know the time horizon. So these three components, I know. So by using this formula, we can simply solve for it. So by using the formula, we can do something like this. So K1 plus P over 100 to the power of N. And let's say I have S. I want this to be equal to S, and S is my target savings. So how would I figure out how much should I put in the bank? I know S, I know this one, I know this one. Yeah, so what should I do with this formula? I know S, I know P, and I know N. Some numbers that I know, yeah? Yeah, exactly. What we need to do, we need to solve. So we need to solve for K. So all we need to do is equivalent to solving for K. So in this case, this is just S divided by 1 plus P 100 N. And this is equal to K. Right? We can also write it in a slightly different way. We can write it as S times 1 plus P or 100 minus N. And this is K. The K is the initial amount. Right? I can write the division in terms of the negative power. That's just an alternative way of writing things down. So especially when we put things into this form, then it's very clear why we need negative powers. because it could be just, strange in the first place. Why do we need negative powers? Well, negative powers appear everywhere where we need to solve, for instance, for initial amount. And the important thing is that this equation is linear, right? We talked about linear equations. You move things to one side, move things to the other side, divide by something, and get x. In this case, it's k. So this is a linear equation. All we needed to do is just divide. That is it. The important bit, that this is a linear equation. That's why it's quite easy to solve. We just needed to divide s by this amount, because this is just a number. We know interest rate, we know n, so we can compute the whole thing here. That's not a problem. So I was planning to stop here, but I had a good question before the start of the class. What if we changed the information that we know to this? So I'm not going to solve this example, but let's think together. So now, let's say I know S, so I know that the target savings. I know the target savings. Let's say I know K, so the initial capital, I know the initial amount. And let's say I know P, so interest rate, I know that one. So now, given that I know these three parameters, how to figure out n? That's an important question. So the question is, how to find n? Right, so I have k, 1 plus p 100, n equals s. And I need to find this. So we're going to learn how to solve this in a few lectures, because this is a very nonlinear equation. So you have your unknown hanging somewhere in the power. So if you need to solve for power, then this is way more difficult. So I use this example as a motivation that we're gonna look into this type of equations and we're gonna learn how to solve them. But if you want to solve them now, so this is coming later in the course. But if you need, for some reason, to solve it now, I can give you a hint. Look up natural logarithm. After I said it, many people just felt relieved for some reason. Yeah, so look up natural logarithm, and you can solve this equation. So this is coming. And the idea here of mine was to just show you that some equations are really very simple. You can just solve for k, like here, just by dividing s by a number here. But it can become very difficult very quickly if we just change the unknown. So now our unknown is in the power, and it becomes a very highly nonlinear equation. So you need different techniques to solve this equation. And we will have a look how to solve this equation, or this type of equations, in a couple of classes. So we're going to get there. All right, so that's what I wanted to do with these examples when it came to powers. And now I want to proceed again to systems of equations. So the second thing, I want to solve a couple of systems again and talk to you about situations when maybe we can immediately see when system has a solution so that it's worth solving it, or maybe it doesn't have a solution, so we may not even engage in solving it, and we can just write there is no solution. That is it. So systems of equations. Let's revise a little bit and let's again see a couple of ways how to solve the same system. Like this. So let's have a few examples. Let's say I have 2x plus y equals 5, and I have x minus y equals 1. And this symbol here, this little snake here, this basically just means that x and y, both unknowns, need to satisfy both equations simultaneously. So if I have x and y, I insert them here, they need to produce 1. If I insert the same values here, they need to produce 5. So they need to satisfy both equations simultaneously. That's why this symbol here, this is important. It tells you that you need to look for a very special pair of numbers. So again, we can just give names. This is equation 1, this is equation 2. So how would you propose solving it? There are a couple of ways, as we know. So how should we start, you think? Yeah, we can do that. So the first step when it comes to these linear equations, if we don't know better, we need to remember that it's easy to solve linear equations. It's easy to swap things around. So what about we focus on equation 2 right here, and then we do this, that from equation 2, we can simply write that x is equal to 1 plus y. So I can solve for x in this equation. I take minus y, move it to other side, and of course minus turns into plus. Right? So, okay, we have x. So I know that x is 1 plus y. So now once I have this expression, I can take it to the first equation. And if I insert it instead of x in the first equation, I eliminate x altogether, and then I'm just left with equation expressed purely in y. And then we can solve for y. Okay, so that sounds like a good idea. So we know from equation 2 that the value of x is 1 plus whatever y is. Now we go to equation 1 and just substitute it in. So this is going to be 2 times 1 plus y, and then I have plus y equals 5. So in this case, here, it's just our x. We just substituted. We substituted x. I'm going to write it explicitly. We just substituted x. And now the whole equation is in terms of y. So then this is just 2 plus 2y plus y equals 5. Right, what we do, we just multiply things out by opening up the brackets. And this gives me 3y equals 3. Right? Because I can immediately take 2 and I can send it to other side. And we have plus 2, so that turns into minus 2, so 5 minus 2 is equal to 3. And now this is all good, because we just divide by 3 on both sides, and we have that y is equal to 1. Okay, so now we come back to our expression of x. So come back to x equals 1 plus y. And then we just insert y. So it's 1 plus 1 equals 2. Right? We just take y that we have solved for and substitute in right here. And then it gives us 2. So then the answer is x equals 2, y equals 1. Like this. Yeah, so you can look into you can look at it quite algorithmically, right? So you take any equation, express one of the variables. We expressed x right here. We could have expressed y, and then we would have inserted the value of y right here, and then we would have gotten exactly the same answer. That's the same method of solution, right? So it's by substitution. We focus on one equation, and then we express one of the variables, and then substitute back. We solve for a variable, we substitute back. There is another way of solving it. So let me go to a new page. So, second attempt. Let me repeat the system. 2x plus y equals 5. X minus y equals 1. So maybe you remember the second way how to solve it? It's a bit quicker, by the way. Yeah? Sorry? Exactly. You just combine both into one. So that's way quicker. You can take this one, and you can take this one. So effectively, you are taking the left-hand side, and you can take the right-hand side. And you just add left-hand sides and right-hand sides of both equations. Right? Because this must be equal to this. This must be equal to this. So if you add this and this, it must be equal to 5 plus 1. And that's just the way it is. It has to be equal. So then if you add both equations, then it's going to be 2x plus y plus x minus y equals 5 plus 1, like this. So in this case is the left-hand side of equation 1. In this case, it's left-hand side of equation 2. Here it's right-hand side of equation 1. This is right-hand side of equation 2. And this immediately gives us the same what the first step in the first solution method gave us. So that is going to give us 2x plus x equals 6, right? Because y and y just disappear. I have plus y and I have minus y, so they just cancel out. So I have that 3x is equal to 6. And of course, if I divide by 3, I have that x is equal to 2. Right? And now I can simply solve for y. So now I can come back to any equation. So come back to any of the equations. Any of the equations. So let's say this could be, which one? Yeah, maybe this one, equation 2. So we call this 1, we call this 2, so we can just return to equation 2. From equation 2, I have x minus y equals 1. So then I know that x is equal to 2. I have 2 minus y equals 1. So it's pretty clear that y needs to be equal to 1, as we already know. So it's the same answer. X equals to 2, and y equals to 1. Yeah, so the two solution methods, they're fairly similar. But also the second one, if you notice it, it's quite similar. So in this case, we notice that both x and y, they have different signs. So then we can, if we add equations, these two will disappear. That was the idea. Okay. So let us learn a couple of facts, a couple of general facts about the systems of equations. I'm gonna give you exercises on Monday from systems of equations to practice. So, general facts. So firstly, we have this form, right? So we have a times x, let me write the unknowns in red, plus b times y, and that's equal to c. And now I have d times x plus e times y, and that's equal to f, right? So these are unknowns, and a, b, c, d, e, f, they are just some constants. Just like here. This is a, then implicitly here we have 1, which is b, then c is equal to 5. Here again, d is equal to 1, e is equal to minus 1, and f is equal to 1. So the coefficients and the free numbers, the constants, they are these coefficients. A, B, C, D, E, F. That's the general form of a system with two equations and two unknowns. And an important thing is that you can show that whatever we did in the examples, so you can show that the solutions that we achieved either by the first or the second method, they have the following form. X is going to be equal to c times e minus b times f divided a times e minus b times d. That is x. And then y is going to be similar. So it's going to be a times f minus c times d. And then the denominator is the same. E times e, a times e minus b times d. So you can simply plug in numbers from the example that we had before, and you will see that x is 2, y is equal to 1. So that's the general pattern. If you have 2 by 2 system, 2 by 2, I mean 2 equations, 2 unknowns, then x and y, they're going to have this form of solution expressed in terms of our coefficients, a, b, c, d, e, f. And given this form, now we can make some conclusions. For instance, when the system does not have a solution. So we can make these observations. All right, so let me go to the first case, no solution. So when you look at these expressions, maybe you can give me a hint. When do you think the system is not going to have a solution? And you should focus on these two expressions. X and y, they are expressed entirely in the coefficients of the system. So maybe we can say something about the coefficients that ensure there is no solution. Sorry, somebody there? Yeah, exactly, yeah, it's just that. So if the denominator is 0, so a times e minus b times d is equal to 0, then we know there is no solution. So no solution when we have the situation of ae equals b times d. So this translates simply into denominator in the x, y expressions is 0. Let me write this into another line. Expressions are 0, is 0. So example, where you can immediately say that there is no solution. So for instance, in the exam, I put forward an example and I tell you solve it, but you know, if you recognize this, then you can immediately tell me that there is no solution. So for instance, we have something like this. X plus y equals 2. X plus y equals 5. So in this case, a is equal to 1, right? Because we have 1 right here. What is b? Well, b is right here, right? b is right here. It's in front of y. So b is also equal to 1. Then I have, what do I need? I need e. So e is right here, is 1. Sorry, I needed to look at the laser. E is 1 here as well. And then d is also 1. So all of these coefficients involved in this little rule are equal to 1. So then clearly, AE equals BD, because 1 times 1 is equal to 1 times 1. So then there is no solution immediately. There is no such pair of x and y that satisfies both equations. When you look into this equation, just at the first glance, do you need to even go through all of this? When you think about it, you look at the equations. Like, do you really need, in this specific case, do you need to go through every coefficient or not? No, why? Exactly, I wrote equation, or I wrote a system in such a way that, follows the rule, but it's a contradiction, obviously. X plus y needs to be equal to 2, but at the same time they need to be, well, the addition thereof needs to be equal to 5. So obviously there is no solution. You cannot satisfy both of them simultaneously, but then you see that in this case, indeed, A times E is going to be equal to B times D. So this is one of the cases. 2, infinitely many solutions. Infinitely many solutions. Let's take it after the break.